Alright, welcome back. What we're going to talk about now is the heating curve, and we're still in section 5 here of chapter 11, and we made it to page 505, and actually what you see on the screen here is figure 11.30, so 1130. And you'll notice what this graph is actually showing us is what happens when you add heat, that is when you add energy in terms of kilojoules to a substance. What happens to it? In this case, we're starting with a liquid, and we're adding heat, and as we add heat it continues to warm up that liquid to a new temperature. Okay, we've seen this equation before when we were talking about thermochemistry. Q, that is heat, equals mass times the specific heat times the change in temperature. Okay, usually we're talking about change in temperature in terms of Kelvin, but since it's a delta T, it's going to be the same thing whether you calculate it in Kelvin or in Celsius. And notice, because it's a delta T, if it was just a regular T and we were plugging in temperature, we'd have to be very careful about whether we were in Kelvin or Celsius. It would make a big difference. So Q here being the amount of heat is just going to be equal the mass times the specific heat times the change in temperature. And that's going to determine how high or how much the temperature changes when you add a certain amount of heat. So we've done this before, like when we had a block of aluminum with a certain mass, we wanted to know what will its temperature change to if you add a certain amount of heat, or say you add a particular amount of heat, what will be, or how much heat will you have to add to change its temperature, and so on, back and forth. Okay, so here we have a liquid, and we're starting off with it at 20 degrees, and we're going to add some heat, and that heat added will go to changing the temperature. And it'll be a different amount. If you take the same amount of heat, the same amount of kilojoules, and you put it into a block of aluminum or into a sample of water or into isopropyl alcohol or anything along those lines, that same amount of heat will cause a different temperature change in each of those materials because they all have different heat capacities, or this specific heat, C sub S. Okay, so we're adding some heat, and as we do that, the temperature is changing. Now, the temperature continues to change up until we reach a point where we have a phase change. In this case, we reach the boiling point, and notice the boiling point starts when we get to 100 degrees. Now, if I continue to add heat to the sample, what is it doing? It's causing boiling. It's causing that phase change, and all of the heat I'm adding goes to boiling and not to continuing to change the temperature. Okay, so once you reach the boiling point, all the heat that you add is going to continue to phase change all of the material present. Okay, so imagine you have a whole cup of water and it starts at 20 degrees. You add some heat up until it gets to 100, and now that water is starting to boil. It's converting from the liquid phase to the vapor phase, and all the heat that you're adding continues to allow that sample to boil until all of that liquid is turned into vapor, at which point then if you continue to add heat to the vapor, you can increase the temperature of the vapor higher and higher and higher. All right, but all the heat you're adding during the phase change only goes to cause the phase change itself. The temperature will stay constant at 100 even though you add more heat, because that extra heat is going to boil your sample. All right, so that's why we see a flattening out or a plateau here in this graph of temperature and heat added. Now, the interesting thing about this is we're going to develop some ideas using delta H vap and how that relates to pressure and temperature changes. We're essentially going to look at the Clausius-Clapeyron equation. The Clausius-Clapeyron equation is very useful for us because it allows us to find things like the pressure or the vapor pressure at different temperatures, and that relates to the enthalpy of vaporization. So we can find that delta H vap term by doing some experiments. We don't always have to look it up every time we need it. Now here you see a boiling, the normal boiling point of these different substances. As their temperature increases, remember they're not going to boil, or they're not going to normal boil, until they've reached the atmospheric pressure, which for us at sea level is 760 torr, 760 millimeters of mercury, or 1 atm. When the vapor pressure reaches that external pressure, it starts to boil. So the boiling point of these different liquids is noted here on the graph. And notice it's 100 degrees for water, it's 78.3 for ethanol, and so on. And we can use this information actually to model the substance a little bit. Since we know this is a curve, Notice it's not a straight line graph. We actually see a curve in here. We can fit it to a mathematical function. Okay? You could do this with any kind of data, but in this case, the vapor pressure is equal to this exponential term. Okay? That's why it was kind of curved. All right, it's not so important that you know exactly where this equation comes from, but just know the different pieces are here for a particular reason. This beta is a constant that depends upon the type of gas that you have. Delta H of vaporization, we saw that earlier. That's something that tells us about how much energy is required to vaporize a particular sample. We've seen R before. That's the gas constant, 8.314 joules over mole Kelvin. Notice it's a little different than when we used it in the gases chapter. T is the temperature in Kelvin. That means we need to convert the temperature to Kelvin before we use it. And P here, of course, is our vapor pressure. So here's how all these things relate. Now, the interesting thing about this equation, although I know it's a little overwhelming if you don't like math, is that we can rework it using ideas about math to a really useful place, which is what we're going to do next. So we're going to, from this equation, which is kind of a fit to the experimental data we just looked at, we're going to mathematically transform it to a very useful form. Okay, you don't necessarily need to know how to do all this, although I think you do know how if you spend some time thinking about it. But notice the transformation that we're making. Okay, I'm not going to ask you to do this on a homework or in an exam, but it is a mathematical process that you can do. Okay, so take the natural log of both sides. That's how we're going to get rid of the e. We separate it out a little bit, and notice since they were multiplied here inside the parenthesis, that means you can add the log of the two pieces. And now notice on this side, since the natural log canceled out the e, we're left with minus delta H of vaporization over R times T. And that's the key term we're looking for here. So we're going to just rearrange this equation algebraically to look like this. And we call this the Clausius-Clapeyron equation. Okay, notice we're taking the natural log of the vapor pressure value and we're taking 1 over the temperature. Okay, those are our key pieces of information which we can use. If we have those pieces of information that we could actually measure them in the lab, that would allow us to experimentally determine the delta H of vaporization, or the enthalpy of vaporization. Okay, so we can go from two things we can measure in the lab easily to a plot to build to find out what the actual value is for delta H of vaporization. So you should remember this equation. It's pretty useful for us. Let's work with it a little bit. Since it tells us how the vapor pressure relates to the enthalpy of vaporization and the temperature, we can find out the enthalpy of vaporization at different temperatures. We could see if it changes. We could figure out what the vapor pressure will be at a different temperature if we know the delta H of vaporization. Or we can find out what the temperature must be if I measure a particular vapor pressure for a certain substance, and things along those kind of lines. So here's what a problem will look like using the Clausius-Clapeyron equation, at least in the first form. We're going to make a graph of the natural log of the vapor pressure versus 1 over the temperature. Notice it makes a straight line. Okay, we're plotting the natural log of pressure and 1 over temperature. 1 over temperature is on the x-axis. Notice it's in units of Kelvin. And the log of the pressure here is pressure in millimeters of mercury. Okay, it makes a straight line, and the equation showed us that the slope of that line is the delta H vap over R. Okay, negative enthalpy of vaporization divided by R, the gas constant. So if you're able to make this plot and fit a straight line to it and find out what the slope is just rise over run, so you could actually take 2 points here on the graph and you could calculate the slope. And from that slope you would set it equal to minus delta H vap over R. So multiply R across and you're going to be left with delta H of vaporization for a particular substance. A really great and useful tool. Okay, the slope of this particular line is minus 3,478 Kelvin. I'm going to set that equal to negative delta H vap over R. Okay, so I'm going to multiply R across, and it looks like this. And then I multiply R, 8.314, times the slope, which we determined was 3,478, and we get out what the delta H of vaporization is. Notice our units is joules per mole. It needs to be in joules per mole. It will come out in joules per mole because R had joules in it. Okay? So it's a really useful experimental way to determine delta H of vaporization, and it has more uses than this, which we'll see coming up. All right, so let's practice here. Determine delta H of vaporization for substance dichloromethane given its vapor pressure and temperature data. So what you did is you walked into the lab, you got a sample of dichloromethane, and you measured its vapor pressure at different temperatures. And from that experimental data, you're going to be able to determine the delta H of vaporization because you know the Clausius-Clapeyron equation. So you wrote all that data down in a spreadsheet, in your lab notebook, and then in a spreadsheet, right? And you wrote down the temperature in Kelvin and the vapor pressure that you measured in units of torr, or millimeters of mercury. And then you took the inverse of that temperature. You took 1 divided by 200 and you got 0.005. You took 1 divided by 220 and you got 0.00455. And you did that for each of those things to make this column of the inverse temperature, 1 over the temperature. Remember, that's what we're going to put on the x-axis. So we need 1 over temperature. And then on the y-axis, we're going to put the natural log of the vapor pressure. So you recorded what the vapor pressure was, and all you need to do is take the natural log of 0.8 and you get minus 0.2. Take the natural log of 4.5 and you get 1.5. Take the natural log of 21 and you get 3.0. And in each of those situations, now all we have to do is plot these two things where the natural log of vapor pressure goes on the y-axis and the inverse of the temperature goes on the x-axis. So when you make that plot, you expect to see a straight line like we just saw in the previous slide. And the slope of that straight line will be equal to negative delta H of vaporization over R. Okay, it sort of sounds like a lot, but all you're doing is recording numbers, and then you're taking the inverse and the natural log, and you're making a plot, and from that plot you're going to see a straight line, and from the slope of that straight line you're going to be able to determine delta H of vaporization. Now I realize this is a lot of information, and there are some homework problems related to this, but it's so much information I wouldn't expect you to do one problem on the exam, for example, that has you do this entire process on your own. You might do bits and pieces of it, but you're not going to have to start from scratch data and develop the delta H of vaporization in the same way. Okay, so now we're making our plot. Notice what we're putting on the x-axis, the inverse of the temperature, or 1 over the temperature, which we already calculated. And on the y-axis, we're putting the natural log of the vapor pressure. And that makes a straight line. Now what's the slope of that straight line? Well, the slope is rise over run. So how does it rise from one point to the next? From one point to another point, it's going to have the same rise because it's a straight line, and divide that by the run. So you want to know what's the difference in y, that's the rise, and then what's the difference in the x, that's the run. So take the rise and divide by the run to get the slope. Okay, or since we're using a computer here, we can just fit a straight line to it. When we fit a straight line, it will show us the equation of that line. So here you see y equals minus 3776.7 times x plus 18.719. This is the equation of a straight line. Y equals mx plus b, if you'll remember from your college algebra days. Okay, so we know the slope of the line now, given to us automatically by the computer, and that slope is minus 3776.7. This number right here times x is the slope. Okay, remember x for our graph and for this equation represents the inverse of temperature. So x is just 1 over t, and y is the natural log of the vapor pressure. That means this slope right here, this number, has to be equal to negative delta H of vaporization over R. So I'll just take that slope and set it equal to minus delta H vap over R. Okay. Then all I have to do is multiply by R to find out what delta H vap is. So R is 8.314. Take that slope, set it equal here. So multiply 8.314 across. Notice the negatives cancel each other out. And that leaves me with the delta H of vaporization, which is 3.16 times 10 to the 4 joules per mole. And in this case, I converted to 31.6 kilojoules per mole. So we're able to determine something very specific about this sample, dichloromethane, based upon making measurements in the lab. Now, why do I care what delta H of vaporization is? Because it will tell me how much heat I have to put in order to vaporize my particular sample. Remember the heating curve? It plateaued. How long is that plateau going to be, and how much heat will you have to put in to get past that plateau? Delta H of vaporization tells you. Now, this equation is sometimes more useful in its two-point form, and there is a little bit of math to get there. We're not going to talk about all that, although we've made it to page 507 where this equation is given, and we're going to work an example problem with it. Now, the two-point form of the Clausius-Clapeyron is really useful for us because if we know a pair of data points here, the pressure at a particular temperature, pressure at a particular temperature, we can solve for the unknown pieces. So if you know delta H of vaporization and you know the vapor pressure at one temperature, what will be the vapor pressure at a new temperature? And this equation will let you solve that directly. Okay, so we'll work some examples to show you. Now, this is great for us because it allows us to find out what the vapor pressure will be at a particular temperature, or what temperature is needed in order to produce a particular vapor pressure, if it's possible to reach that. Okay? Calculate the vapor pressure of methanol at 12 degrees Celsius. Now, the first thing I'm noticing is this is degrees Celsius. I need to work in degree Kelvin, so I'm going to have to make that conversion. And I have methanol here, so I'm going to look up the delta H of vaporization for methanol is 35.2. Now, where'd that number come from? That's kilojoules per mole. Either I was given that from a table, I looked it up in the back of the book or in the CRC handbook or on the internet, or maybe previously I was in the lab and I measured the vapor pressure at particular temperatures. So if I measured the vapor pressure at different temperatures, then I had to build a plot, find the slope of that plot, and set that slope equal to minus delta H vap over R to solve for what delta H vap is. Maybe I already did all that. Or maybe I just looked it up, okay? So now that I have that number, I have the temperature and the normal boiling point, 664.6 Celsius, and the pressure at 760 torr, okay? So what am I saying here? I'm saying using the two-point form of the Clausius-Clapeyron equation, what I need to do is use the data from delta H of vaporization and a pressure related to one temperature, a vapor pressure related to one temperature. Then I can solve for the pressure at a new temperature, which is what I'm doing here. I want to know the pressure at my new temperature of 12 degrees C. Okay? So I go and I look up methanol, and I look up its boiling point, and I find its boiling point is 64.6 degrees Celsius. And I know automatically, if that's its normal boiling point, that the vapor pressure has to be 760 torr, or atmospheric pressure at sea level. So I automatically have, if I look up the boiling point, what the vapor pressure is at that boiling point, if it's the normal boiling point. And I have the delta H of vaporization, so I know the second temperature that I want. Now I can solve for the other piece of information that I'm looking for here, which is the vapor pressure at a new temperature. Okay, so using that, we're going to find this vapor pressure at the new temperature. We're going to plug it into the two-point form of the Clausius-Clapeyron equation. And look here, we've got the natural log of P2 over P1. And we're multiplying by this 1 over T2 minus 1 over T1. So be sure that your P2 on top corresponds to your T2 on the left-hand side here, left. T2 and P2 have to go together, just like P1 and T1 have to go together, because that'll make the equation easier for you to solve. Okay, so convert your temperatures to Kelvin, because that's what works in this equation. So I convert temperature 1, which is the boiling point, and that's 337.8 Kelvin. And I convert temperature 2, which is 12, to 258.2 Kelvin. Now I have both of those temperatures in Kelvin. I'm going to put them into my equation. Notice also here that my delta H of vaporization is 35.2. That's kilojoules per mole. So I'm going to want to make sure I keep track of my units. Alright, so keeping track of my units and plugging in values, notice I converted my delta H of vaporization to joules per mole. Why? because I have R in terms of joules, 8.314 joules over mole Kelvin. Okay, so I want to make sure that my joules and my joules cancel. If I plugged in that number in terms of kilojoules, I'm going to get the wrong answer. So I've got Kelvin, Kelvin, joules per mole, Kelvin. So everything will cancel out nicely. And I just want to make sure that my units of pressure are the same units on the top and the bottom. Okay, in my case, we're using torr or millimeters of mercury. But notice I can plug all these things, which are just numbers, into my calculator to get one value. And I can set the natural log of P2 over P1 equal to one number, minus 2.31 here. Okay? Now all I have to do is solve this equation when I substitute in the value of P1, which is 760 torr. So I get P2 divided by 760 torr equals e to the minus 2.31. You may be saying, wait, what's going on here? Well, notice in this case, let's see if I can write on the screen here. And notice in this situation, in order to get rid of the natural log, I'm going to take e and I'm going to make it an exponent of e. And since I did that on one side, I have to do that to both sides. So I put that e in here, which means the natural log and the e are going to cancel and go away, leaving me with P2 over 760 equal to e to the power of minus 2.31. Okay, that's where this expression comes from. Hopefully that makes sense. Okay, so P2 over 760 equals this. This is something you can plug into your calculator, find the e button, and take e to the minus 2.31 power, and you should get this number. Okay, then take 760 and multiply by this number, and you get 75.4 torr. So the vapor pressure of methanol at 12 degrees C is 75.4 torr. And the reason you're able to know that is because of the 2-point form of the Clausius-Clapeyron equation, because you know what delta H vap is, and because you have a vapor pressure temperature point, which you found just by looking up the normal boiling point. Determine the vapor pressure of water at 25 degrees C. Okay, so we're going to do the same thing here, except with water as our sample, which is maybe a little bit more familiar. The delta H of vaporization for water is 40.7 kilojoules per mole, and I know its boiling point is 100 degrees C, and that means its vapor pressure will be 760 millimeters of mercury at 100 degrees C. So I want to find it at 25. I'm going to do the same thing I did before, the 2-point form of the Clausius-Clapeyron equation, except now I'm going to plug in the numbers for this problem. Okay, convert both of my temperatures to Kelvin. I get 373.2 and 298.2, and I'm going to make sure that I'm associating T1 with P1 and T2 with P2. But since all I have are numbers on this side, and notice my units, I made sure that was in joules and this is in joules, so we want to be consistent. Plug all this into your calculator to get one number, and that one number then you can set equal to the natural log of P2 over P1. Now to get rid of that, what are you going to have to do? Same thing we saw in the last problem. You're going to have to make it an exponent of e. And when you do that, the natural log cancels out, if you'll remember the algebra here. And that's going to leave us with a situation where we have e to the minus 3.30 power, which is equal to P2 over 760. So multiply 760 by this decimal here, and you find out what the pressure is, which happens to be 28 torr at 25 degrees C. Okay, so you can find the vapor pressure at any new temperature you want because of the 2-point form of the Clausius-Clapeyron equation. Now that's a really useful skill, and it's probably the most difficult math, certainly the most difficult we've done in this chapter, because it's the first really math that we've done here. Anyway, we'll talk more about how all these phase changes and stuff work in the upcoming videos.